In previous videos, we took this bivariate data and we calculated the correlation coefficient. And just as a bit of a review, we have the formula here. And it looks a bit intimidating, but in that video we saw all it is an average of the product of the z-scores for each of those pairs. And as we said, if r is equal to 1, you have a perfect positive correlation. If r is equal to -1, you have a perfect negative correlation. And if r is equal to 0, you don't have a correlation. But for this particular bivariate data set, we got an r of 0.946, which means we have a fairly strong positive correlation. What we're going to do on this video is build on this notion and actually come up with the equation for the least squares line that tries to fit these points. So before I do that, let's just visualize some of the statistics that we have here for these data points. We clearly have the 4 data points plotted, but let's plot the statistics for x. So the sample mean and the sample standard deviation for x are here in red, and actually let me box these off in red so that you know that's what is going on here. So the sample mean for x, and it's easy to calculate, 1 plus 2 plus 2 plus 3 divided by 4 is 8 divided by 4, which is 2. So we have x equals 2 right over here. And then this is one sample standard deviation above the mean. This is one sample standard deviation below the mean. And then we could do the same thing for the y variables. So the mean is 3, and this is one sample standard deviation for y above the mean, and this is one sample standard deviation for y below the mean. And visualizing these means, especially their intersection, and also their standard deviations, will help us build an intuition for the equation of the least squares line. So generally speaking, the equation for any line is going to be y is equal to mx plus b, where this is the slope and this is the y-intercept. For the regression line, we'll put a little hat over it. So this, you would literally say y hat. This tells you that this is a regression line that we're trying to fit to these points. First, what is going to be the slope? Well, the slope is going to be r times the ratio between the sample standard deviation in the y direction over the sample standard deviation in the x direction. This might not seem intuitive at first, but we'll talk about it in a few seconds, and hopefully it'll make a lot more sense. But the next thing we need to know is, all right, if we can calculate our slope, how do we calculate our y-intercept? Well, like you first learned in Algebra 1, you can calculate the y-intercept if you already know the slope by saying, well, what point is definitely going to be on my line? And for a least squares regression line, you're definitely going to have the point sample mean of x, comma, sample mean of y. So you're definitely going to go through that point. So before I even calculate for this particular example, where in previous videos we calculated the r to be 0.946, or roughly equal to that, let's just think about what's going on. So our least squares line is definitely going to go through that point. Now if r were 1, if we had a perfect positive correlation, then our slope would be the standard deviation of y over the standard deviation of x. So if you were to start at this point, and if you were to run your standard deviation of x and rise your standard deviation of y, well, with a perfect positive correlation, your line would look like this. And that makes a lot of sense, because you're looking at your spread of y over your spread of x. If r were equal to 1, this would be your slope, standard deviation of y over standard deviation of x. That has parallels to when you first learn about slope, change in y over change in x. Here you're seeing you could say the average spread in y over the average spread in x. And this would be the case when r is 1. So let me write that down. This would be the case if r is equal to 1. What if r were equal to -1? It would look like this. That would be our line if we had a perfect negative correlation. Now what if r were 0? Then your slope would be 0, and then your line would just be this line. Y is equal to the mean of y. So you would just go through that right over there. But now let's think about this scenario. In this scenario, our R is 0.946. So we have a fairly strong correlation. This is pretty close to 1. And so if you were to take 0.946 and multiply it by this ratio, if you were to move forward in x by the standard deviation in x, for this case, how much would you move up in y? Well, you would move up r times the standard deviation of y. And as we said, if r was 1, you would get all the way up to this perfect correlation line. But here it's 0.946. So you would get up about 95% of the way to that. And so our line, without even looking at the equation, is going to look something like this, which we can see is a pretty good fit for those points. I'm not proving it here in this video. But now that we have an intuition for these things, hopefully you appreciate this isn't just coming out of nowhere and is some strange formula. It actually makes intuitive sense. Let's calculate it for this particular set of data. M is going to be equal to R, 0.946, times the sample standard deviation of Y, 2.160, over the sample standard deviation of X, 0.816. We can get our calculator out to calculate that. So we have 0.946 times 2.160 divided by 0.816. It gets us to 2.50. Let's just round to the nearest hundredth for simplicity here. So this is approximately equal to 2.50. And so how do we figure out the y-intercept? Well, remember, we go through this point. So we're going to have 2.50 times our x mean. So our x mean is 2 times 2. Remember, this right over here is our x mean. Plus b is going to be equal to our y mean. Our y mean, we see right over here, is 3. And so what do we get? We get 3 is equal to 5 plus b. 5 plus b. And so what is b? Well, if you subtract 5 from both sides, you get b is equal to -2. And so there you have it. The equation for our regression line. We deserve a little bit of a drum roll here. We would say y hat, the hat tells us that this is the equation for a regression line, is equal to 2.50 times x minus 2. And we are done.